Hello students, welcome to Saurav Sir's classes. The problem that we have in hand today says let an be a sequence e to the minus 2n times sin n and bn be the sequence e to the power minus n times n square times sin n whole square for n greater than or equal to 1. Then the options are sum over an converges but sum over bn doesn't converge, sum over bn converges but sum over an doesn't converge, both of them converge, or neither of them converges. So we basically have to find out which of the two series converges. Now we know that sum over an converges if sum over mod an converge. If sum over mod an converge, we say that the sequence is absolutely convergent. Now mod an equal to mod of e to the power minus 2n sin n, but mod of sin n less than equal to 1 implies this is less than equal to mod e to the power minus 2n. Therefore sum over mod an is less than equal to sum over e to the power minus 2n, which makes it a geometric series, and when we take e to the power minus 2 common, we get 1 plus e to the minus 2 plus e to the minus 4 and so on. So we get e to the power minus 2 times 1 by 1 minus e to the power minus 2. So we get a finite constant here which is equal to the sum of mod e to the power minus 2n. Therefore sum over mod an would be less than this, and hence this is convergent. Now we have to check the convergence of the other series, which is bn e to the power minus n square sin n whole square. Now bn plus 1 by bn is equal to e to the minus n plus 1 n plus 1 square sin n plus 1 whole square by e to the minus n square sin n whole square. Now this is equal to e to the power minus 1, because e to the power minus n gets cancelled out, times n plus 1 by n whole square times sin n plus 1 by sin n whole square. Now to apply the root test in this situation, we just have one problem, the sin n plus 1 and the sin n terms. So to solve the problem, what we do here is bn is less than equal to e to the power minus n times n square. If possible, we can just take mod bn less than equal to this. So if sum over e to the power minus n square mod converges, it implies that sum over mod bn converges, which implies sum over bn converges. So we can just deal with this term now. Now if we call Cn to be mod e to the minus n times n square, Cn plus 1 by Cn is just E inverse times n plus 1 by n whole square, which is equal to E inverse times 1 plus 1 by n whole square. Now limit Cn plus 1 by Cn as n goes to infinity is E inverse times 1, because 1 by n goes to 0 and this entire term goes to 0. beg your pardon, goes to 1. So this goes to e to the power minus 1, which is less than 1, and by root test sum over Cn converges. Therefore sum over Bn converges. So both An and Bn converges, and C is your correct answer. Now let us move on to the next problem. The next problem says let fx equal to x sine square 1 by x if x is not equal to 0, and 0 if x is equal to 0, and gx be x sine 1 by x, x not equal to 0, and 0 if x equal to 0. What we have to check is differentiability at 0 for both the functions f and g. So now limit as h goes to 0, h sine square 1 by h is equal to limit as h goes to 0 sine square 1 by h, which does not exist because 1 by h goes to infinity and sine square hence becomes an oscillating function. Since this limit does not exist, f is not differentiable at 0. For g, limit h goes to 0, h sine 1 by h gives us limit h goes to 0 sine h times sine 1 by h. Here sine 1 by h is an oscillating function as h goes to 0 because 1 by h goes to infinity, but sine h goes to 0. Since sine 1 by h is less than equal to 1, this limit is equal to 0. Therefore, we see that g is differentiable at 0. So g is differentiable at 0, but f is not differentiable at 0, and hence B is the correct answer. Thank you. For any doubts in the video, please post in the comment section.